Okay, uh, welcome back to the video. Now, in the last videos, we have discussed uh, the dish method and the washer method to help us compute the volumes of the objects that created by spinning some regions around the axis. Okay, now we continue with the next part where you uh, will learn about the cylindrical shell method. I mean, in the previous video, uh, we spinning curves, we spinning regions around the x-axis. So what if we're spinning regions around the y-axis? Okay, so let's suppose that you still have some function f of x, and the functions um, when you're plotting the function, you have some curve, and the question try to limit the regions from A to B. So you have some region R like this one, and you're spinning this thing around the y-axis. So the objects you're gonna have gonna look like this. Okay, and the question is, how do we compute the volumes of these things? Okay, so it is a little bit different compared to the washer method, but the idea is still the same. You're gonna discretize your regions, but how do we discretize things? Okay, so for instance, let me consider just uh, the very thin rectangle that contain inside the regions, and if I spinning this thin rectangle around the y-axis, I will have something look like the the cylindrical shell. Okay, so that means initially the objects that you have when you're spinning the regions around the y-axis, they are just this thing. It's just the combination. I mean, you will have a bunch of cylindrical shell stacking together. Okay, so again, you try to discretize the solid that you have into something. And so if you want to compute the volumes of this thing, you're gonna compute the volumes of each cylindrical shell, and then you're gonna add them together to get the volume of the objects. Okay, again, you still use the ideas of discretizing stuff. Okay, in this way, in this scenario, instead of discretize into a bunch of slices, you're gonna discretize your objects into a bunch of cylindrical shell, and then you're gonna compute your volumes of this cylindrical shell, and then you add them together to obtain the volumes of the objects. Okay, so let's focus on the main questions. How do we compute the volumes of this cylindrical shell? So the idea is if you want to understand this thing, I want you to use a bit of imaginations. So let's suppose that I cut this cylindrical shell and then I flatten them and I flatten it out. Okay, this is a cylindrical shell. I use a scissor to cut it out, and then I flatten them out, and we have something like a super thin rectangular box. Does it make sense? We use the scissor to cut this thing out, and then we flatten it out. We will have something like the rectangular box. Okay. If you are not understand at this point, maybe you can pause the video and use a bit of imaginations. Okay, you have the cylindrical shell, and then you cut it out, then you will have something like a super thin rectangular box. Okay, and because this thing is the rectangular box, to compute the volumes of this thing is not a big problem. You just need to figure out 3 dimension of that thing, and then you take the product of 3 dimension. You're gonna have the volume for the rectangular box. Okay, so firstly, for the thickness of the box, the thickness of the box is just the thickness of the cylindrical shell. Okay, and the thickness of the cylindrical shell is just the base of this rectangle, and this is just the length of your discretization. So that is delta x. Okay, the length of your discretization. Next things, the height of the box. Okay, the height of the box is just the height of your cylindrical shell, and technically, when you spinning these things around the y-axis, the height of your cylindrical shell is just the height of this rectangle. And again, the height of this rectangle is only determined by the output of the function. So that means for the height of my thin rectangular box, it should be the output of the function f of x. Okay, we have the first dimension, which is the thickness, and this is delta x. The height of the box, which is f of x. The only thing left is the length of the rectangular box. So technically, this thing initially coming from this circle, right? Because you're spinning this thing around the y-axis. So technically, the length of the box is coming from this circle. So if you want to compute the length of this box, you need to compute the perimeters of this circle. And the perimeters of the circles of radius are, okay, the perimeters is 2 pi times the radius. Okay, so what is the radius of this what is the radius of this circle? The radius of the radius of this circle is just the distance from this rectangle to the y-axis. Okay, and technically this is just x. The distance from the box to the y-axis is just x. So that means I take 2 pi times x to get the perimeters of this circle, and the perimeters is the length of the box. So that's why I have 2 pi times x over here. So that means the volumes of this thin rectangular box is 2 pi x times f of x times delta x, because this is the box, this is a rectangular box. So if you want to find the volumes, you just need to take the products of these three dimensions. Okay, and then, like I said, you discretize your volume into a bunch of cylindrical shells. And for each cylindrical shell, you can compute the volume by doing this way. So to compute the volume of this thing, you just need to take the summations over a bunch of cylindrical shell. And again, if you take the summation, if you take the infinite sum of this thing, you're going to have the integral from a to b of 2 pi x f of x dx. Okay, so let's do one example to demonstrate the ideas of cylindrical shell method. Okay, over here, you have the regions bounded by the curve x squared plus 5, the line x equal to 0, the line x equals to 3, the line y equal to 0. So this is the region you have. And you're going to spinning this thing around the y-axis. So if you're spinning this thing, you're going to have something like this one. Okay, I just draw it out to help you get the better visualizations. Okay, but the point is you just need to use these things. Okay, so again, you have to, if you want to compute the volumes of something, you have to figure out three things. You need to figure out the lower bound, the upper bound, and the function. Over here, the function is x squared plus 5. So we good. So far, we good. And the point is, the question also giving us the lower bound and the upper bound. You can see this is the lower bound, this is the upper bound, and you're spinning this thing around the y-axis. So your volumes is the integral from the lower bound to the upper bound of 2 pi times 2 pi times x times f of x. So times x times function f of x, which is x squared plus 5. I have x squared plus 5 dx. Okay. And now I believe things is straightforward now. 2 pi over here, just constant. I can take it out. And I'm gonna distribute x into this parenthesis. I have x squared. I have x times x squared, so I have x cubed. I have x times 5. It means 5x. Okay. I haven't taken integral yet. I just distribute this thing into the parentheses. Now we will take the integral. The antiderivative of x cubed will be x to the power of 4 divided by 4. We add 1 to the power, so 3 plus 1 give me 4 divided by new power. Then 5x will give me 5x squared divided by 2. We add 1 to the power, so 1 plus 1 is 2. We divide it by 2. And then we're gonna evaluate this thing as the lower bound and the upper bound. Again, you plug in 3, and then you plug in 0. So the final result should look like this. 3 to the power 4 divided by 4 plus 5 times 3, 2. 3 squared divided by 2 minus 0. Because I believe that if you plug in 0 into these two things, you just simply have 0. And then you can use your calculator to get the final result for this one. So, okay. And so this is the ideas how you use the cylindrical shell method to compute the volumes of objects when you're spinning some regions around the y-axis. Actually, there are several justified versions for the cylindrical shell method as well. The first version is, over here, I consider the region that created by one curve. So what if we have the region that created by two curves? So, the idea should be similar. So let me go through the question. In this question, they want us to find the volume of the solid obtained by rotating the regions bounded by two curves, y equal to x and y equal to x squared around, it should be around the y-axis. Okay, so you have, this is the line y equal to x, and this is the curve y equal to x squared, and this is the regions created by these two curves, and you're gonna spin these regions around the y-axis. Okay, so you spinning things around the y-axis, you're gonna use the cylindrical shell method for sure. But the point is, initially, for instance, over here, like I said, you have some objects, and then you just retire it into a bunch of cylindrical shell. And over here, the height of your cylindrical shell is given by the output. But over here, thing is a little bit different. Again, you still have some rectangle. If you just retire the region, you still have some rectangle. Okay. And the point is, you're gonna spin this rectangle around the y-axis to have the shell, to have the cylindrical shell. So the point is, the height of your shell is not simply given by f of x anymore, because this rectangle, in in these pictures, the shell, the height of the shell is just simply given by the output of the function f of x. Okay, there is no limitation in the lower part of your rectangle, but over here there are some limitations. Okay, so that means if you want to find the height for your cylindrical shell, you should take the output of the upper function, subtract the output of your lower function. Okay. So again, so initially, I mean, the original versions of your cylindrical shell method is 2 pi times x times f of x dx. So up here, I mean, initially we discussed that this is the height of the shell, okay? But over here, the height of the shell is a little bit different. You have some lower bound, I mean, you have some limitation in the lower part of your rectangle. So instead of using f of x over here, I mean, instead of using f of x, you have to take f of x subtract g of x to get the height for your cylindrical shell. Okay, so the uh, the the upper function over here, the upper function is x, so I have x. Okay, the lower function is x squared, so I take x subtract x squared to get the height for my cylindrical shell. And over here, I mean, every other thing are still similar. You need to find a lower bound. You need to find the upper bound over here. The lower bound is 0. The upper bound is 1. So you have the integral from 0 to 1. You still have 2 pi times x. Okay, you still have 2 pi times x. But you have to justify a little bit to fit in this question. This question, the region is bounded by two functions. So instead of using instead of just using f of x, you have to use f of x subtract g of x to get the height for your cylindrical shell. Okay, and then things will be more straightforward. You just need to distribute x into the parentheses. You have x squared minus x cubed dx. Okay, and then you have to find your antiderivative, which is x cubed. Oh, sorry. Um, you have x cubed divided by 3 minus x to the power of 4 divided by 4. And then you need to evaluate your antiderivative at the lower bound and the upper bound. Okay, now we have 2 pi. You plug in 1. You plug in 1 to these things. You have 1 cube minus 1 over 4. Subtract the values of the function at 0. But again, when you plug in 0, you're going to have 0. So I just minus 0. Okay, and then you can use your calculators to finish your to get the final result. Okay, so this is the first justified version for the cylindrical shell method, where you have some limitation for the height of the cylindrical shell because now you have two curves, so the height of your cylindrical shell will be the difference between the output of these two functions. So you will take the upper function, subtract the lower function to get the height for your cylindrical shell. The other justified versions of the cylindrical shell method is instead of spinning around the y-axis, you're gonna spinning around some other vertical axis. In this scenario, I want you to find the volume of the solid obtained by rotating the regions around the line x equal to -1. So this line, not the y-axis. Okay, I want you to spin this region. I want you to spin this region around the y-axis. I'm sorry, around the line x equal to -1. Okay, and again, so you still starting from your we still start from our cylindrical shell method, which is this one. Okay, so initially the thing you have a 2 pi times x the x. Okay, I'm sorry, 2 pi x times f of x dx. Okay, this is your original cylindrical method, but this is applied when you spinning spin when you're spinning stuff around about the y-axis. Now you have the question want you to spin the regions around the line x equal to -1. So things is a little bit different. Okay, firstly, I mean, you're still spinning this thing around the line. So the height of your cylindrical shell is still given by the output of the function. The only different things is the parameters of your circle. I mean, initially, for instance, for this one, when you spin this rectangle, around the y-axis, the if you want to compute the parameters of your cross sections, you would take 2 pi times x because x is the distance from the rectangle to the y-axis. But up here, because you're spinning things around the line x equal to -1, so that means beside the distance from x to the y-axis, you should add one more unit. You should add one more unit because now you're spinning stuff around the line x equal to -1. So up here, I still have 2 pi. Okay, to compute the volumes. To compute the volume, I still have 2 pi. Okay, the height of my cylindrical shell is still given by the output of the function. Okay, it's still given by the output of the function. But the point is, the parameters for the cylindrical shell should be x with one more unit. Okay, so I will multiply by x plus 1 instead of x. Okay, so I want to emphasize that you have to justify the original version of the cylindrical shell method in this way. Instead of x, I have x plus 1 because now I'm spinning things around the line x equal to -1. So I add one more unit to my radius. Okay. And then things were still the same. In this question, you are not given the lower bound and the upper bound. So to find the lower bound and upper bound, you can see that you just need to find the intersection between these two things, the line y equal to 0 and the green curve over here. So you let them equal to each other, you can find the lower bound at 0 and the upper bound at 2. Okay, the lower bound is 0, upper bound is 2. Okay. Now I'm gonna replace. Firstly, I bring 2 pi into the front because it's just a constant. I will write x plus 1 again. And my function is 2x minus x squared. So I have 2x minus x squared dx. Okay, I have 2 pi 0 to 2. Okay, and I'm gonna expand the product between these two parentheses. So x times 2x, x times 2x give me 2x squared. X times x squared give me negative x cubed. 1 times 2x give me 2x, and 1 times negative x squared give me negative x squared. Okay, we simplify it. So 2x squared minus x squared give me x squared. I rewrite x cubed again, negative x cubed. And rewrite plus 2x again. And now we just need to find the entire derivative. So again, this is just power rule. 2x squared divided by 2. And you need to plug in the upper bound and lower bound. So again, the lower bound is 0. When you plug in stuff, they are just 0. Then you plug in 2. you will have 2 pi 2 cubed divided by 3 minus 2 to power 4 divided by 4 minus 2 times 2 squared divided by 2. I mean, I would say you have to subtract the values of the function at 0, but when you plug in things, they are just 0. So you have 0. Then using your calculator, you can get the final result for your calculation. So this is the cylindrical shell method. So again, you still use the ideas of discretize your objects into a bunch of cylindrical shell, and you're gonna compute the volume for each layer of your cylindrical shell. And you're gonna have some justified versions like what if the region is bounded by two curves? What if the region is rotated around some different vertical line rather than the y-axis? So in the first scenario, you will adjust f of x as f of x minus g of x because the height of the rectangle is uh, is the difference between the upper curve and the lower curve. In the second scenario, instead of using x as the radius for your cylindrical shell, you have to add one more unit because you are spinning stuff around the line x equal to -1. Okay, so this is pretty much the things we have for the cylindrical shell method, and I will see you in the next video.